All right, in this video lesson, what we're going to look at is a different way to write functions, okay? So a function, again, is all about inputs and outputs. Inputs are the things that we're plugging in, outputs are the things we get out of it. So the way we're familiar with it is representing the input as all my x's and my output as all my y values. So this is what's called standard notation, where y again represents the output, x represents the input, and we can write, for example, this is a linear function of y equals 2x plus 5. This is known as a function rule because it explains what I am doing to my input in order to receive my output. All right, so what this means again is that if I were to plug in a value for x, it'd be 2 times some number plus 5, and that's going to give me here my output, which is y. Function notation is just a different way to write the same thing. What you're going to see in function notation is this symbol, f parentheses x. This is not a mathematical expression, but instead it's just a symbol to represent the word function. So the way I like to think about this is that the word f represents function. So the way you say this is f of x. F stands for function, so think of this as function of x. What it does is it just explains the rule that is going on with my x values, which is my inputs. So it focuses strictly on the 2x plus 5, and again within this, x represents my input, so that doesn't change, but f of x here is just going to represent my output. So simply what we are doing is instead of writing y when we would write in standard notation, we're writing f of x. So know that y and f of x literally mean the same thing. The only thing that's different is in function notation, we're going to see our inputs and outputs labeled differently. In standard notation, let's say that I were to plug in the number 1. So that would have 2 times 1 plus 5. That's going to give me 7 as a result. And the way we would express this is that if my input is 1, my output is 7. Standard form, we'd normally express it as a an ordered pair of x and y. In function notation, I would do the same thing. I'm still going to plug in my number 1, 2 times 1 plus 5, and that would give me 7. But the way this is going to be written is like this. F of 1 equals 7, where 1 represents my x and 7 represents my y. Again, that's my input, and that represents my output. So it's going to be labeled differently, but it's almost the same thing that we would do for a point, just represented in a different way. So our goal for today is to represent function notation, to be able to understand how to evaluate function notation and to read function notation. So the first thing we're going to do is evaluate. So let's say I give you a function f of x equals negative 4x plus 7. So when I give you x equals, say, a number, like here x equals 2 or x equals negative 2, what this means is I am giving you what's called the input. So I'm giving you an input of 2 and an input of negative 2. When I give you an input, what we're trying to do is we're trying to figure out what would I get as an output when my input are those values. So anytime you're given an input, what you're doing is you're going to input that number into the function where you see x. Now the way this is going to be written is it's going to say, okay, f of my input 2. I'm going to try and find what would my function be equal to, what would be my output when my input is 2. That's going to equal negative 4 times 2 and then plus 7. And all I'm focusing on is this part of my function right there. Negative 4 times 2 would give me negative 8, plus 7 would give me negative 1. So when I plug in my output of 2, what I get is negative 1 out of it. This right here, oopsies, this right here is my input, and this is my output, okay? What we might be familiar with is instead of writing in function notation, we would normally see this as 2, negative 1, where again, 2 is my x and negative 1 is my y. That is standard form. But again, function notation is going to represent That same idea, just written a different way. So if I were to plug in -2, it's the same thing. I'm going to do -4 times, in this case, -2, and then add 7. By simplifying that, -4 times -2 is +8 because they're both negative. Add 7, I'm going to get 15. So now writing this in function notation, when my input was -2, my output is 15. So again, what goes inside here? This is going to represent the input, and then this is going to represent the output. And again, this is how I would write it in function notation. Would be the same thing as writing this as a ordered pair of -2, 15. So understanding that when we look at function notation, it's going to be written a little bit differently. So let's see if we can understand how to read that. So here I have a relationship between the outside temperature and the number of hours after 6 a.m. So we're going to look at the meaning of these statements written in function notation. So we're going to let f of t, which is our output, we're going to let f of t be the outside temperature. So this is going to be our output. And then we are going to let t hours, that's going to be my input. So the number of hours is going to be my input. So when I read this, let's say f of 0 equals 58. That is saying that 0 is my input and 58 is my output. So what that means in total, that we're looking at 0 hours after 6 a.m. And what that's going to tell me is that my temperature is 58 degrees Fahrenheit. Now, what does 0 hours mean after 6 a.m.? What this means is that at 6 a.m., the temperature is 58 degrees Fahrenheit. And the second one says f of 6 equals 65. Again, 6 is my input, 65 is my output. So 6 right here in parentheses is going to represent the number of hours, and then 65 is going to represent the temperature. So here, I'll show this in blue, 6 hours after 6 a.m. would be 12 o'clock p.m., or we'll think of that as noon. At noon o'clock, the temperature would be 65 degrees Fahrenheit. And in our last example here, I'll show in green. This one says f of 3 less than f of 9. So real quick, this is again the less than symbol. So what this is telling me here when I read this, that f of 3, f of 9, this would be 3 hours after 6 a.m. This would be 9 hours after 6 a.m. So 3 hours after 6 a.m. would be at 9 a.m. and 9 hours would be at 3 p.m. Now, what is this statement saying right here? When we're looking at f of 3 and f of 9, that is strictly telling me about the output. So what this is saying here is that the temperature at 9 a.m. is going to be less than the temperature at 3 p.m. Okay? So reading function notation is a little bit different in how it looks, but again, it's going to tell us the relationship between that input and that output in terms of specific values. All right, now this one's going to be a little confusing because it's going to look a little bit different, but now it says we're going to, for a given function, find the value of x. So if you think about inputs and outputs, one of our previous examples, what we did is I gave you guys an input. I told you that x equals this, and what you did is you plugged that number in and you got an output. Here, you are given the function of h of x equals 2/3 x minus 5. But instead of giving you a value of x, I'm telling you to find the value of x. Okay, so we're going to find the value of x, which means we are going to find the input, and here you are given an output. So the way we're going to do this is we need to first read this a little bit differently. My function is 2/3 x minus 5. Now, when you're given the output, I am not taking that number and plugging it in there. But instead, what I'm going to do is try and figure out what value of x would I plug in order to give me -7. So what would be my input if I were to have an output of -7? Now, this is something that you could possibly think through, but I'm going to show you guys how we can use some tricks and trades that we learned before on solving equations to try and get this answer. If I were to treat this as an equation, I could just do my inverse operations by first adding 5 to both sides. So I would be left with 2/3 x equals -2. And then I have myself a fraction, so to get rid of this fraction, I'm going to multiply by its reciprocal, 3/2. I'm going to multiply this side by its reciprocal, 3/2. By doing that, again, the reciprocal is going to make those cancel, leave me with just x. -2 times 3/2 would then give me -6/2, which simplifies down to -3. So what this means then is that for this given output, my input would need to be -3. So in terms of function notation, f of -3 would give me -7. I give an input of -3, I will have an output of -7. Again, standard form would show us to write it as -3, -7. But again, when thinking about it, just kind of think through it in terms of inputs and outputs. Okay, when you're given your input, you can find your output, and when you're given the output, you have to kind of think through and solve it like an equation to find the input. All right, last two examples here. We're going to look at how to represent a function graphically, and then we're kind of put it all together for a little modeling problem. So here you're given a function of f of x equals 2x plus 5. So now we're going to represent a function on a graph. So again, treat the f of x as our y values. So notice I have here a table of values. X is going to represent my inputs again, and y would normally represent my outputs, and now here's written f of x. So again, that's still going to represent my outputs. How a function works again is we're going to determine what things we're going to plug in, and then we're going to try and figure out what we'd get out of it. So in any given function, we're going to choose our inputs. So I'm going to choose some inputs that are centered in my graph around 0. So I'm going to choose the inputs of -2, -1, 0, 1, and 2. I like to do that because these values, again, are centered around 0. It's going to give me some values to the left and to the right. Now, when I try and graph a function, all I'm going to do is take these inputs and I'm going to plug them into my function where I see x. So I have 2 times x plus 5. So all of these numbers here would go where this number is here. Okay? And that's then going to tell me what I get as an output. So that again is going to equal f of x. So for example, if I were to plug in -2, 2 times -2 plus 5 would give me an output of 1. If I plug in -1, 2 times -1 plus 5 would give me an output of 3. If I plug in 0, 2 times 0 plus 5 would give me 5, and then I would have 7, and lastly 9. And notice the rate of change here between my values. It's +2, +2, +2, and +2. So notice I have a constant rate of change, which means that when I plot these points, I'm going to recognize that these points would form a straight line. So again, this would be considered a linear function, just representing that linear function in function notation. All right, now let's kind of put this together in a real-world example. So here I have a graph of a helicopter's first flight that shows the distance it travels over a certain number of hours, and it's representing the distance it is away from its destination. So say my destination is Madison, Wisconsin, and I got to travel there via helicopter, which would be pretty neat. To start off with, it's showing here in the graph that the helicopter is 300 miles away, and then 3 hours later is when it would reach its destination, shown here as 0. So notice the graph is going downward because it's starting 300 miles away, and it takes 3 hours to get there. So this is the first flight. It says here then on its second flight, the helicopter travels 50 miles farther and increases its speed by 25 miles per hour. And here it says the function 350 minus 125x would represent the second flight. And I want to know then, first of all, what would this graph look like, and then which one would take less time? So again, any sort of function, what we're going to do is choose values to input to figure out what our outputs are. I'm going to choose inputs shown here on the graph. The distance traveled depends on the time, as shown here. Okay, f of x is the number of miles, and x hours. So think of hours as my inputs, and then my miles as my outputs. Okay? So I'm going to choose then inputs, and I'm going to choose it from my graph. I'm going to go 0, 1, 2, 3, and 4. So I'm going to look at 4 hours here total. And what I'm going to do is I'm going to plug each of these numbers into my function. And my function rule that's given is 350 minus 125x. So what I am plugging into is I'm plugging in for x to try and figure out then what my output would be. So plugging these inputs starting from 0 all the way to 4, I would get the following outputs. I get 350, 225, 100, negative 25, and negative 150. Now, real quick, the last two numbers do not make sense if you think about it, because then that means it went beyond its destination. So between 2 and 3, it's obviously going to reach its destination. So I'm going to plot these on my graph. There's 3 points that I can explicitly show. I have 0, 350. I have 1 and 225, which would be here. I have 2 and nothing but hundreds. And then 3 would be at negative 25, which would be somewhere below my graph. So I know then that when I connect these dots with this line, boom, you see that. And it wants to know then which flight takes less time. Well, obviously, if I look at my values here, and I can view this on my graph, the first flight took exactly 3 hours to reach its destination. But notice how right here the points intersect, the two lines cross each other. And beyond this, you'll see that the green line would hit the x-axis first, which means it reaches its destination a little bit before 3 hours, a little bit less than 3 hours. So in this case, which flight would take less time? In this case, the second flight would take less time based on what I'm seeing, not only from the values, but also from the graph. So in this, we just looked at the idea of function notation, how to express things in function notation, how to read them, how to evaluate them, and then how to apply this to our idea of linear functions. So again, if you've got any questions, make sure you jot those things down, and we'll see you guys next time.